Ready to go. Excellent. It's a pleasure to be here today. And actually, I think John already gave it away in my bio, or actually I gave it away in my bio, talking about property graph databases and how I think that they are actually rocking it. But what I want to talk today about is fair data principles and how graph databases are actually probably an extremely good framework to implement these principles in your data stores. And before I talk about, what the fair data principles are, and before I talk about, graph databases, I thought just give a brief introduction why we need it. And truth there is quite simple, right? Okay, here we go. For some reason it wouldn't progress. Our relationship with data has fundamentally changed since the beginning. I mean, when we developed drugs in the early days, I mean, we obviously have our value chain from discovery to market and sales. And in the early days, really what happened is we just handed the drug candidate, along this value chain, like on a conveyor belt. And what happened to data was very simple. It was just stored, in each of these phases. It was just a means to an end. It wasn't really valued that much. But today, obviously, we know that data is at the center of it. And what we're trying to do is really to make data available throughout the organization, available for everybody who needs it at any given time, so that they can make their informed decisions. And the aim really is therefore to make data and the knowledge that comes from data explicit. So it's making everything really available and explicit to everybody. So that's one point. The other point, obviously, is that we've realized that data actually has a value beyond its initial creation. So we want to reuse data at a later stage. And in order to achieve that, what we actually have to do is we have to make sure that these original observations, findings, or whatever we are actually capturing is stored in such a way that when we retrieve it at a later stage, we can actually infer exactly what we originally observed. Because if we can't do that, if we can't actually make sure that what we see at a later stage, what we read at a later stage is the same that we actually originally captured, we can't use it anymore. So it is very important that we actually make sure that our data is, described very well with all the context that it originally came with. And obviously that's where the whole fair data principles come in. So fair data obviously is, FAIR is an acronym, and it stands for these 4 things here. So if you talk about findable data, it obviously means that data needs to be uniquely identified, but it also means that we can make sure that the data we see is actually relevant in the context to what we want to do with it. Accessible, there are various levels of accessibility. I mean, obviously there is the physical accessibility, you need to have an internet connection or whatever to actually access the actual database. Then there is a user accessibility. So we need to make sure that only those people who are supposed to have access to particular data have access, and we need to, manage these usage rights. But then there's obviously also a structural accessibility, I call it, which means that you need to be able to understand what the actual database, the data looks like, how it is, organized, so that we can actually query it and access it from that perspective. Interoperable. I mean, this really means that the data that is, there is understandable from a content perspective. So, that everybody knows a spade is a spade, a study patient is a study patient, and so forth. So that everything, that the content is well described. So again, that people can understand it. And that really goes towards terminologies and controlled vocabularies. And fourth, there is this reusability aspect. I mean, obviously, as you can see from this arrow, I don't see it very much as a principle as such. I think it is more of an outcome of these other 3 principles that we have. So that is all about the fact that you basically have the data, well described with the context it was created in and so forth, that you can actually reuse it. And the main aspect I think that is relevant here is that everything basically revolves around the metadata that you connect and collect and describe in relation to your data. Now, there are two other things I want to mention here. First of all, when they sort of first came up with these fair data principles, it was very clear that it is not just designed for humans. So in other words, the data needs to be described and stored in such a way that also machines or other software agents can actually access it so that they are able to parse it and work with that data. And the other thing is that it's not a specification. So as it says, these were like guiding principles rather than a technical implementation of how to do it. Nevertheless, when they talk about fair data principles, they have this notion of concepts and data objects. So the way they look at it is that the actual data is sort of contained in these data objects with a identifier, with the metadata and the provenance available to describe the actual data that is contained in this object as well. And when they talk about these objects, they also talk about concepts, which are kind of metal representations of physical entities. I mean, that's the best sort of description I could come up with, and it's like the concept of a bridge. So everybody, when we use the word bridge, we know what a bridge is. When we use the word study patient, we know roughly what a study patient is, and then obviously there are these implementations of these. Now, obviously, the problem we have is that the tools that we have at our disposal, or that we had at our disposal, really weren't really designed to work with these fair data principles. And because what we normally work with is relational databases. And if you look at the relational database, it's effectively a bunch of tables that are connected through arbitrary relationships based on key value, key pairs, and also each table can look very tricky, and you have sort of repeats here in order to show one-to-many relationships and so forth. And also another thing is, we have these field labels which are more or less understandable. So, and then we have the actual data, and again, they're more or less understandable. What a relational database cannot do is it cannot store or tell you anything about the metadata. So you need to store all of this data in a separate metadata repository, or you have to store it in your application logic or wherever to make this work, which makes it quite complicated to work with. But on a rudimentary level, what you could say is that each row in these data tables is kind of a rudimentary data object in the sense of what I've just talked about with the fair data principle. And if you take these rows and sort of convert them into individual objects, you're pretty close to a property graph. So here now you have these individual objects, or nodes as they are called in graph terminology, which have a label which already identify what this node is about. So this node is about the clinical study, and you have all the properties available that are related to that particular clinical study as part of the object. And we know then that this clinical study has patients. So here we have 2 patients, and again they have their own properties, and which you can then actually look at. And and patients have other sort of things like adverse events, and again you have the fields and the properties related to these fields. And just for reference, I mean, if you talk about RDF, which is sort of, I think, the most used graph technology at the moment, this is then a further step away from property graphs, where you actually have a complete atomic decomposition, and everything is based on statements. You have your main entities here, which represent sort of, something. This is the URI, Universal Resource Identifier. You have the statement that this is a study and that that study has an indication, and so forth. But based on my intro, obviously, it is my opinion that graph databases aren't created equal, and particularly in the context of what I'm talking today, I believe that the sweet spot really lies with property graphs. Now, talking about these individual sort of objects, I mean, at the moment, they don't really look very much different to a row in the relational database I showed earlier. And so the question is, okay, what's the benefit? And if you look at the FAIR data principles, it's all about metadata. And that's really where graph technology or property graph databases come into their own, because you can have a situation where you take your object, which at Capiche we call holons, which is semantics. You can actually enrich these objects with metadata. So for instance, you can add to the adverse event as such, you can add metadata, describing exactly what metadata, what an adverse event is. We have the concept, it belongs to the concept of adverse events, what type of holon it is. You can also add classifications to your holon or your data objects. In our case, for instance, we use the Dewey Code, which effectively is a library cataloging system, which has all the sort of hierarchy of where books originally belong and research belongs, and then it's very detailed. So you already know all the, you can also store all the metadata relating to what an adverse event is and how that works. But you can go further. So for instance, you can also look at the individual properties, and you can store the metadata associated with those as well. So if you look at severity, again, you can have a description of what severity is. You can also talk about synonyms, so which makes it potentially more readable to different people, because AE/SAF is perhaps okay for a machine, but severity is definitely much easier to read for a human. You can have all the other information, type of data, it's a string, whether, what type of content it is, it's ordinal. You can even have the full vocabulary, attached to it. So we know that severity can have mild, moderate, severe. So when you actually look at a particular adverse event, which is mild, you also know what other options there would be. And you can even see, what might be interesting for a machine, because a machine wouldn't know what the difference between mild, moderate, and severe is, but it would know that, okay, if you tell it that it goes from better to worse, that severe is not as good as mild. So in other words, you can create data objects which are very much enriched by the metadata you need to understand this data and better. And obviously, because it is part of the actual object, so it never gets separated. When you look at that object, you have all the information available to understand that information directly. So it is kind of self-describing. It is whole in its own. And that's why we actually call them holons. Now, this slide is only there to show you that, because when you talk about FAIR data principles, it's all about humans and machines. And you can obviously describe the information presented in these holons, for instance, here as an XML object, or you can use JSON. So in other words, it is very well designed so that it is also available to be parsed and understood by machines. Now, from the picture I showed earlier, I mean, obviously the data object is one thing, but an object doesn't make a database, and important there is also that you have relationships, and then I've already showed that a little bit. That, studies can have patient in before. So starting with the adverse event that I talked to. So you obviously can have lots of these data objects, and only by looking at the label, we already know what they are about. So the label already gives you a very good indication what it is all about. And then obviously you can then connect these individual data objects through relationships, which can either have or cannot have higher meaning. I mean, that's, I think, for instance, one of the big distinctions I would make between property graphs and RDF, that property graphs provide a little bit more flexibility when it comes to the modeling, because the focus is on the objects, not so much on the relations, whereas with RDF, the focus is very much on the relations in my opinion. So by doing this, you can actually then create an ontological data model, which is a formal representation of a particular knowledge domain or a clinical study or whatever it is you want to model. And therefore, again, as it is a formal description, can be used as, for people to actually create a common understanding what's going on. So if everybody agrees on what the ontology looked like, and everybody is therefore then singing from the same hymn sheet. Because it is formal, it also makes it more interoperable, because everything is well described, everything is defined in a way that everybody can understand and agree with, which then obviously makes the data more understandable. Therefore, then it makes it more analyzable. That's the word. And therefore, it can be easily shared amongst people and machines. And when you then take this model, and just as an example, when you then take that model, what you end up with is a model that you can then instantiate for each data point. And since you look at the patient perspective, you then have the data for each patient and the instances of each patient, so you can create a patient-centric view. But I'll talk about that in a second. You can also create other views. Now, one other aspect I want to talk about is accessibility and data querying, because I mean, we all know SQL is not exactly a very simple language, and it means that you have, if you use multiple tables, it becomes quite complex to actually sort of create an SQL statement, because you have to link all the tables. You need to understand exactly what the data model looks like. And then, for instance, to ask a simple question like this, what adverse events have been reported for patients with elevated liver values, would probably, create quite a complex SQL query. Actually, it does, and I've got another slide for when I haven't got time for it here. But from a graph database perspective, it becomes actually quite simple, because the graph, as it is self-describing in many ways, the relationships, within the graph are present as part of the graph. You can actually look at a patient and say, like, okay, here we have the patient, and we want to look at all the liver values, which are above a certain value. And then what you want to do is you want to return all the adverse events that are associated with that particular patient. And therefore, the query is very much intuitively related to your question, which obviously makes it much, much simpler to do. Apart from that, you also have a situation where you can actually exploit that further, and what we call data reflection. So also which adds another level to the accessibility of your data. And if you look at something like this question here, where you basically have a property B with a value Y, and the query for that property, for that value in Y, without reflection, that's kind of the data that you would get back. So it's this tree of the data that you would get back. But then if you add a certain reflection point or perspective to it, so for instance, we reflect in the patient, so we want to have a patient perspective, and we say, okay, you do the same query here, you also get then effectively back all the data that is related to that patient. So you get back all of that data, including obviously the study, because obviously the patient was also part of the study. So this is the way where you can ultimately easily sort of create cohorts for your data, and you can easily also change the perspective. So you can move it to the study. For instance, if you have study programs where you basically analyze studies as a whole, you can do that as well. So that's as much as I want to talk about graph databases. And now, just to summarize it all, how does it relate to the FAIR data principle? So If you look at findability, I hope I could convince you that actually property graph databases provide a means to create these data objects with rich metadata, and obviously they're all uniquely identifiable. So data within your system should be, well described, findable. When it comes to the accessibility, the fact that graph databases can be underpinned by ontologies and ontological data models makes them effectively self-describing, which makes the accessibility from that perspective very easy. Also, if you look at other things like user accessibility, obviously you have far more granularity because technically you can actually sort of decide at what level a user has access. So has he access at the database level or at the individual sort of data object model. So for instance, when it comes to privacy, you can sort of fade out data that people shouldn't be seeing in this context. As far as interoperability is concerned, because everything is described either by formal ontology or controlled vocabulary, graph databases obviously lend themselves to interoperability. And since they all match these, things, obviously graph databases are also a clear, contender when it comes to storing data for reuse, because obviously data is described as a realistic presentation, and therefore, allows effective reuse of the data. And with that, I would like to finish, and I hope I convinced you that graph databases are in effect, rocking. Thank you very much.